Yes, so I'm Enrique del Barco. I'm a professor in the physics department. I've been at UCF for the last 15 years. I'm currently Associate Dean in the College of Sciences. I take care of research. And I was looking for a photograph of me with beer, but I didn't find any official one. I only have very old ones, so I chose this one. That shows one of my hobbies, that is playing guitar. All right, so this is a look of my group. If you're interested in learning a little more of the details, you can go to the webpage. I have 6 amazing graduate students and 2 postdocs. These 2 guys in red are postdocs, and an undergraduate student who has joined my group very recently. And we basically focused on very, very fundamental physics problems, but I always look for something that also very fundamental because it's really poorly understood, also allows for some long-term applications that could perhaps change the current technologies. I work on 3 different projects. I'm going to go through each of them individually. The first one is the one that I have been working forever. I started doing my PhD in Barcelona, working on molecular magnetism. I only have 1 student now working on this, but it's a very sophisticated, difficult, slow advancing project. The field, just to give you a quick summary of how the field is on this arena. This basically is a single molecule that has some magnetic ions inside, and the whole molecule behaves as a single nanoscale magnet, like an atomic magnet. And as a result of that, the spin projection can be either up or down. And because of intrinsic anisotropy in these molecules, these 2 states are separate. And as a result of that, we have been investigating this for a couple of decades. We fully understand more or less how the basic behavior of these spins is. But as a result of that, they have been proposed for quantum bits, magnetic quantum bits. So this is, a very good part of the effort within the community is to understand the quantum dynamics of the spins in these molecules and see how to implement quantum logic operations with them. In particular, we're interested currently in my group in understanding how to use spins in these molecules that are coupled by exchange interaction, and then how can we implement quantum logic operations in these dimers, either spectroscopically by applying pulse of microwave radiation, optically by using ligands that allow us to tune the coupling between the 2 qubits optically, or more recently, we're also investigating some dimers that allow some electric control of the exchange interaction. I have a number of collaborators. This is not all of them, a couple of them at UCF, and this is funded by the NSF. The techniques that I use for that are very low temperature. We have the lowest temperature at UCF. We can go down to 15 millikelvin degrees. And in particular, we do magnetometry, very high sensitivity magnetometry in Hall effect sensors that we fabricate ourselves out of 2-dimensional spin gas materials. We could also do microwave spectroscopy real time with pulses down to 50 millikelvin. And we use very high sensitivity, high power superconducting resonators with nanoscale constrictions in order to improve efficiency. Okay, the other research area is molecular electronics. I have a larger number of students working on that. We have been very successful in this field lately. To summarize the field, well, molecular electronics maybe started a couple of decades ago also. And the first intention was to see whether we can duplicate and eventually replace silicon-based technologies for electronics with the idea of making things more compact because molecules are smaller, right, than the smallest transistor that you can think of. But with time, it's clear now that we will never replace silicon-based technologies, but molecular electronics actually provide functionalities that are alternative to those that you can get from classical electronics, right? In our particular group, we are focused on molecular rectifiers. Actually, we demonstrated a couple of years ago a molecular diode that provides rectification ratios up to 1 million, that is comparable to commercial silicon-based diodes. Most recently, we've been focusing on molecules that provide multifunctional responses. Like, for example, in this case, we published last year in Nature Materials a molecule that behaves as a diode with some rectification of current at different polarities of voltage, but at the same time, it behaves as a switch. That is actually very good, because in one single system, in a single molecule, you have two different functionalities. In this case, a diode and a resistor in series. That is basic, the basic component of a resistive RAM device, for example, right? More recently, we're looking into a little more complicated devices that provide different functionality, more than two functionalities at the same time. This is a project that is well funded currently by the engineering division, the ECCS. And in this particular case, we have seen how we have devices that they show some plasticity, depending on what they have done. They show some memory. Depending on what you have done to them previously, they will behave in one way or the other. It can behave as a resistor, as a diode, or even as a negative differential resistor. And this is, again, with some collaborators here and abroad. The techniques, well, basically, we need to place one single molecule in between two electrodes, and this is not easy. But we leverage on very state-of-the-art facilities here at UCF from nanofabrication. In particular, we do these single electron transistors, in where we have an aluminum gate and two electrodes. Then we make a nanowire that we eventually break. This nanowire is fabricated in Cryol with the e-beam writer. And the last project, that is the one that is taking most of my time right now, is on nanoscale spintronics. So we are not only interested in the conduction of charge through nanoscale systems, whether it's a molecule to a zero-dimensional system, a two-dimensional layer, for example, graphene or any other similar system, or even 3D systems. But also we're interested in how a spin can be, how magnetic moment can be transported through these devices. And in particular, we're actually now looking into the possibility of using antiferromagnets for spintronics. And so let me just give you a very quick summary of what the field of spintronics is now, or has been in the recent times. It all started with the discovery of giant magnetoresistance by Ph.D. and Grunberg. They got the Nobel Prize in 2007 for that, and it has found widespread applications in informatics, in memory storage and reading, and et cetera, et cetera. And this is based on the fact that the current, the resistance of a magnetic system depends on the magnetization of the system. So if you have a magnetization in a particular way, the resistance may be higher than if the magnetization is in a different way. Okay, so this is the basic, without going into any detail, of what magnetoresistance is. So it's basically the flowing conduction electrons flowing through a material will feel the magnetization of the material and react against it, right? So most recently, and I'm still talking about almost 2 decades ago, somebody came with the idea that, well, you know, we just follow the arguments by Newton and the third Newton law, that there is always a reaction to an action, a reaction to every action. If conduction electrons will be feeling the magnetization state of a system, the magnetization state of the system should be also feeling the nature of the electrons flowing through it, right? So if we polarize the current through a material, we can actually act on the state of the magnetization of this material, and this has been given rise to applications in spintronics that are very, very interesting. For example, in a spin valve with a ferromagnet, in where you can control the state of the magnetic device just by current flowing through the device, or even generate gigahertz oscillations in your material by passing current that is magnetically polarized. Well, this allows gigahertz operations in nanoscale spintronic devices. Our goal is focused on replacing ferromagnets by antiferromagnets. Antiferromagnets actually differ from ferromagnets in the sense that they have an energy that controls the magnetic nature of the antiferromagnet that is about 3 orders of magnitude larger than in ferromagnets. So if we can leverage on that energy, we will and find the same applications and abilities that we do with ferromagnets, we should be able to extend the frequency of operation into the terahertz, or the time response of the device into the picoseconds. So we move from gigahertz to terahertz, we move from nanoseconds to picoseconds, and you can just very quickly see the advantages for technologies, right? This is that's what we're doing. We're looking for that. We have already found very, very interesting results that we just published in Science last year. We have a number of collaborators in this case, very, very close collaborators. This is a project that is funded by a MURI grant by the Air Force Office of Scientific Research that we obtained a year and a half ago, $7.5 million in order to advance this topic. And I believe this summarizes, and I'm looking at my stop clock. I have 10 seconds just to show you the technique that we're putting in place. This is a new cryostat and a new split coil magnet 9 Tesla with optical access that is complemented by a quasi-optical terahertz spectroscopy system that allows us to work up to 1.1 terahertz. We're working with Mike Cheney, who is an ultrafast laser expert here in physics as well, because he has the ability to generate electromagnetic pulses of up to 40, 50 terahertz as well. So I would be very interested in finding somebody who can complement our expertise here, particularly when it comes to terahertz and time domain. And this is basically all. Thank you very much.